So welcome everyone. Welcome to back to our S3D seminar series. So today we're very excited to have a talk from one of our own faculty members. Kang is an assistant professor here in the Software and Societal Systems Department in the School of Computer Science here at Carnegie Mellon University. His interests include software engineering and formal methods with applications to systems safety and security. He's interested in developing modeling techniques, design methodologies, and automated verification to construct safe and secure software and cyber physical systems. He has applied his work to a diverse range of systems, including intelligent vehicles, unmanned aerial vehicles, or UAVs, medical devices, water treatment plants, and mobile applications. He is currently co-teaching a very popular software engineering for AI class, which we were just talking about. Before coming to CMU, Eunsuk spent a year working on connected vehicles at Toyota. He earned his bachelor's in software engineering at the University of Waterloo and his PhD in computer science at MIT, where he was advised by Daniel Jackson. And his talk today will be on some of his current work, designing software systems to be robust.
Thank you. Thanks for coming. I know there's like a deadline tomorrow for some of you, so thanks for showing up despite that. I appreciate that. So yeah, if I see. So I'm going to tell you about some of the ongoing work that we're doing in our group, looking at ways to design software that is robust. By the way, before I begin, if you have any questions, please stop me. I would like this to be interactive, so don't feel like you have to wait until the end. So more and more software these days is used to control systems that look like this. So self-driving cars, smart grids, IoT, medical devices. And one common aspect across these systems is that they all closely interact with the physical environment. So these systems, to satisfy their requirements, they typically rely on different types of assumptions about the environment. For example, this may say things like, in a medical system, the nurse must perform some actions in a correct order. The network latency must not exceed some threshold, or maybe the attacker doesn't have access to a secret that could be used to compromise the system. Now, in practice, what happens is that the environment doesn't stay the same, right? It changes over time, or maybe there's some kind of failure that occurs. And as a result of this, the environment could deviate from these assumptions. For example, the nurse once in a while could make a mistake and forget to perform a critical action. The network may experience unexpected failure or disruption, or the attacker may obtain the secret through a side channel they didn't think about. So the question that you could ask here is, does the system still work in these cases? Now, I'm going to give an example of a concrete failure that occurred that I think is because the system was not designed to handle these type of deviations. So this was a radiation therapy system at a hospital in Panama City. And the software for the planning, the treatment was created by a company named Multi-Day Systems. And then the machine itself was created by a company called Electronics, which by coincidence was also the creator of the Direct 25, the infamous radiation therapy machine. I think actually they changed their name after Direct 25 to do something. But anyway, so the way the system worked, so one of the things that have to happen in the system is that before treatment, the system inserts what's called the shielding blocks. So these are lead blocks that are put in place to protect healthy tissues of the patient. And the way this would work is that the patient would draw user interface to draw the shape of the lead blocks. And then based on the shape drawn by the operator, the software computes the final radiation dose. Okay. Now, so as you can probably guess, there are some accidents that occurred. And on the days of the accidents, the therapist was perhaps tired or maybe they're stressed and they made a mistake. So they're supposed to draw a shape that looks like this in a particular order, right? So the one on the left is the correct order of drawing the shape. But then they ended up drawing the same shape in different order, right? So instead of drawing it like this, they, I guess, use a different way of drawing the shape. And for some reason, the software, the dose that was computed by the software was twice the amount that was supposed to be received by the patients. And because of this, 28 patients were overdosed, and 21 of those patients have passed away from this accident. So it was a quite tragic accident. There are many fallouts from this accident. One of them being that there was a lawsuit against the hospital and the company. And the company, multi-data system, they argued that this is not their fault, right? This is the fault, the blame lies on the therapist, because if they hadn't made a mistake and drawn the shape in the correct order as instructed, then this problem would not have happened. So I'm curious actually to hear your opinion on this. Do you think this is user's fault, or do you think this is software's fault or someone else's fault? Who thinks this is user's fault? Nobody. Oh, okay, one person there. One other person, okay. Two people think it's user's fault. Three. Okay,
I will blame the company.
You blame the company, okay. Okay, so anyone else blame the company? Okay. Both, okay, both. That's a fair answer as well, right? So I don't think that's a correct or wrong answer here, but there are different perspectives you can take here, right? So on one hand, the company is technically correct in the sense that if the user didn't make this mistake, if they had drawn the shape exactly the way they're instructed, then perhaps this problem would not have happened. So that's, I think, maybe perhaps a fact. But on the other hand, these nurses and therapists, they're also humans, right? They're not perfect. They're going to make mistakes from time to time. And it seems unreasonable for us that there's never going to be any error made by a human, right? So ideally, what you want is you want to design the system so that even if the user once in a while make a mistake, the system will guarantee some level of safety, right? So that's, to me, at least that's the perspective that I take. But I, can argue about this more afterwards if you're interested. But the outcome of this was that the three therapists that are involved in the accidents were charged with manslaughter and they're barred from practice. So this is a very tragic event overall for everybody involved. So the message I want to send here is that the environment, so in software systems, the environment which they're deployed at some point is going to deviate from the expected behavior, right? So ideally, a system that's robust should ensure its critical properties, right? Even if the system does not function 100% correct, it should ensure some level of safety or security or other critical requirements under such deviations. Now, I don't think this is such a radical view. I think this is actually a fairly common perspective at least in other engineering disciplines. So there is this book that I really like, I recommend, by an American engineer named Haley Petrosky called To Engineer is Human. And he has sort of studied different kinds of engineering systems in the past. And he argues that successful engineering systems are designed with what he calls a margin of safety that protects the system against abnormal events that perhaps you don't expect to take place under normal operating conditions. Right? So how do we do this? Or how do engineers do this? Well, here's 4 easy steps of achieving this. You start by designing an initial or devising an initial system design, and then you identify different kind of deviations in the environment, and then you analyze the system to see whether it's actually robust against those deviations, and if not, then you redesign the system to improve its robustness. And maybe you repeat this process as many times as you need. So the question that I was asking in the early days of this research was, can we do this for software? Right? Can we apply this kind of methodology for software? And what I realized was that we don't really understand exactly what we mean by robustness. Although there's been a lot of work in certain domains like distributed systems or embedded systems, where they have this notion of fault-tolerant design. Across software in general, there doesn't seem to be a definition that people agree on. So if we don't know what it means for software to be robust, then how do you actually verify that it's robust? And also, how do you actually design system or redesign a system to make it more robust? So these are some of the questions I've been exploring in the last few years with my colleagues. So today I'm going to tell you about some of the work that we've been doing to try to answer these questions. So you can sort of think of roughly there's being 3 major components in our research roadmap. First, how do we specify what it means for software to be robust? How do you analyze it, right? How do you actually check that a system is robust? And how do we make it more robust? So we call this robustification, which is the process of taking an initial design and try to improve it to make it more robust. And this is just mentioned joint work with my colleagues. So CJ and Ian, I think they're both here. Yes, they're here. And then David, as well as my postdoc Romulo, who had just started the faculty position at Penn State. So all the good ideas in this talk are from them, and the bad ones are from me. So, yeah. So let me start by telling you a little bit about what we think it means for software to be robust. So here's a high-level idea. The intuition here is that robustness is a property of a system that represents the maximum amount of deviations in the environment the system can handle in the sense that it can satisfy a desired property under those deviations. So let me try to make this a little bit more precise. Me being a formal method person, I like to sort of write things down in Greek letters. So I'm going to share some Greek letters. So suppose that you have some description of the system. Here I call this M, or software specification. And you have some assumptions that you make about the environment. So E here could be a model of the environment. And then P is some property that you want to satisfy. Now, suppose that the environment changes. So there is some deviations here. So the delta represents the deviation that brings the environment to a new environment E prime, okay? And then suppose that the same system still guarantees the same property under this deviated environment. So if that's the case, then we're going to call that the system M is robust against this particular set of deviations delta with respect to the environment E and property P. Okay, this is sort of our basic definition. And I'm going to make this a little more concrete. I'm going to assume that the M and the E are specified using what's called labeled transition systems, or LTS. So LTS, you can think of this as essentially a state machine where you have a set of states and a set of events or actions. They allow you to go from one state to another state. So, for example, this LTS-M represents interface for radiation therapy machine. And then in the initial state, you start from a state called the editing. And then the user could press X for X-ray mode, or E for electron beam mode. And depending on the actions the user takes, you go to a different state. And then you can think of the behavior, the possible behaviors of the LTS as the set of traces they can generate by running that state machine, right? So you can run this state machine by pressing X and then maybe press enter. That's one possible trace. You can also do X, enter, and B. B here is for firing the beam. And again, in general, there could be infinite number of possible traces you could generate from a state machine. Okay, so now you have assumed, okay, we have this M and E's as LTS, and P is some safety property. And then the idea here is that we're going to represent these deviations as traces, or again, some sequence of events that are not in E. Okay, so these are going to be the behaviors that do not belong to E that we're going to be adding to E prime. So this E prime now is a new model that behaves like E, except it has these additional behaviors. It can do more things than the original environment could do. And finally, we're gonna sort of define the overall robustness of the system as the maximal or the largest set of possible behaviors or deviations it can add to the environment, and the system still guarantees the same property. Okay. So conceptually, you can think of this as a kind of a buffer around the environment. So you have your normal environment, and there are things that can go outside of the environment, additional behaviors, and your system will still guarantee the same property under these deviations. And this robustness represents that largest possible buffer or margin that your system can handle. So let me try to give you an example. So far, it's been pretty abstract. So I'm gonna go back to another radiation therapy system. Again, this one probably a little bit more well-known. So the influence there 25. So the way this system works is there's two different kinds of radiation modes. There is the electron mode, which uses electron beam to treat patients. And this is a relatively low power radiation. Whereas there's another mode called X-ray mode, which is high powered, that's delivered to narrow area on the patient's body. So to make sure that the X-ray doesn't go everywhere, the system inserts what's called a spreader. Okay, so that block is inserted into the path of the beam. And then if somehow this block, this spreader, is taken out of the place while the system is still in X-ray mode, and that's going to cause a safety violation. That's going to result in potential overdose for the patient. So that's the outcome that we want to avoid in our system. But in fact, what happened was that this actually happened. So the fatal injuries that are caused by DARC25 was because somehow the system ended up delivering the radiation in X-ray mode, even if the spreader was out of place. So I'm going to tell you about how that could happen. Before that, let me say a little bit more about how we model these systems. So again, going back to this picture here, M here is going to be the model of the DARC25 design. So it could perhaps consist of a model for the interface of the system, as well as the model of the controller that's used to switch between different radiation modes. The E here is going to capture the expected behavior of the human operator, right? So the task that the operator is expected to perform for correct functioning of the system. And the P here is going to describe the safety property we want to ensure, which is that no radiation should happen. So I don't want to go into detail of this state machine. This is one way to model the DARC25 system. One thing I'll point out is that when the system switches between X-ray and the EV mode and vice versa, there is some delay that occurs. So here, suppose system is in X-ray mode, and the user presses E to switch to electron beam mode. Then the system will spend some time in an intermediate state before it completes its transition to the other mode, and vice versa. Okay. Okay, and here is a model of the operator. So this model again captures the expected sequences of user actions. And you can think of this sort of coming out of like a training manual. So if you look at a user manual for a product, it says things like, step 1, you do X, and step 2, you do Y, and eventually you will be able to complete the task that you want to perform. And so this model sort of captures that expected user behavior. And here in this particular model, there's 2 possible choices. So user can either do X, so select X-ray mode and enter, and then press B to fire, or select E and then press enter. So select E to select the EV mode and then press B to fire. Yep. So suppose you have these models, and then the first thing you might want to do is you just want to check whether the system under the perfect environment, so the expected behavior of the user, satisfy the property, right? So that's sort of the basic thing that you want to establish before you start reasoning about robustness. And indeed, if you use a standard model checker and run this through those tools, you will see that the model satisfies the safety property. Okay. So ideally, at this level of abstraction, the system does ensure safety. Okay. So let's now try to introduce a deviation in the environment. Okay. So here I'm going to use I'm going to try to model a particular error that was committed during the DARC25 accidents. So this is coming out of the paper written by Nancy Levison and Clark Turner, which is a great paper on sort of describing the accidents that occurred. So here, what the paper says is that the therapists, so they wanted to treat the patient under the electro mode, but then they made a mistake. So they pressed X first. So what they did was they went back and they pressed up to fix the mistake, and then they selected the E, and then they went on to the rest of the treatment. So we can sort of model this as a, So we can model this deviation basically as additional trace, right? That's not in the behavior of the original model. So in this particular case, X enter B is the expected behavior. And what the user did was they did X first, and they press up, and then they did E then, and then they entered and they press B. Okay. So this is a new trace that we're going to add to our original environment, and then we're going to end up with a new environment A prime. Then you could ask the question, does the system still guarantee safety under this new deviated environment? Okay. And the answer is actually no. So under this particular error, this could lead to a safety violation. So what happens, this is actually what happened in the DARC25 accidents. So the user pressed the E to switch to electron mode. And because user pressed E, the system took out the spreader out of place because the system thought, okay, we're going to treat the patient under the electron mode. And then what happened next was that there was a kind of race condition between the user's action and the system's transitioning from the X-ray mode to EV mode. So user press B to fire, but the system happens to be still in the midst of transitioning to the electron beam mode. So because the system was still in X-ray mode, it fired a high power radiation without the spreader being in place. And this led to the overdose that took place in the actual accidents. I mean, the actual accidents, there's a lot more details and nuances to these accidents for Terra 25, but so I'm just covering one aspect of that, but you can sort of think of this as roughly what happened that caused the radiation overdose. Okay, so the bottom line here is that, okay, the system it wasn't quite robust against this particular error that was made by the human operator, right? So let me try to maybe summarize what I've been talking about for the last 5 to 10 minutes, okay? Here's another way to look at robustness. Suppose you have this box here that represents all possible behaviors of the system expressed as possible traces over some set of events. And we're gonna sort of take this circle here to represent the set of possible behaviors that could be generated by the environment. So this could sort of be, this could consist of some different traces that consist of combination of user actions in the case of Terra 25. And then some small subset of that is going to represent our normative environment. So this is the environment that represents the expected behavior of the user, right? And ideally, hopefully the system satisfies its property under this normative environment. Now, so things that are outside of it, right? Environmental behaviors that are outside of this normative environment, the system may or may not be able to guarantee its property under those environments. So we're gonna split that into two. So things that are in the red are the deviations in the environment for which system cannot guarantee its property. Okay? So we're going to call this intolerable deviation because these are things that can go wrong, the system just cannot do anything about. And finally, things that are in between is what we call robustness, right? This blue area is all the set of deviations that the system is able to guarantee its property. And the sort of the punchline here is that, again, representing these deltas as traces, we can actually compute this as a first-class property of software. So I'm going to tell you more about that in the next slides. Any questions so far? Yes.
Wouldn't some of our formal colleagues argue that M should be the delta circle, not just the white circle?
M should be delta circle.
Question is whether some of our more formal colleagues might argue that the M should have been as inclusive as possible in the first place, so that the M should represent the green circle, not the white circle, or the blue circle, or teal circle, or whatever.
Actually, that's a really good question. My actually response to that is that in general, this blue circle is very small, right? Like you're sort of, in general, most systems that we studied are not that robust, right? You don't really think about what could go wrong. You think about, you're so focused on getting your system work well under some particular assumptions about the environment. So perhaps, I don't know if this answers your question, but what we observed is that in general, this is very small area, right? And this red area is much larger than the blue area. I don't know if that answers your question. But yeah.
How does this definition of robustness work with more continuous spaces? Because like right now we're looking at a trace that follows a specific, discrete set of events, right?
Yep. Mm-hmm. So that's a really good question. And so two answers is that, one answer is there's been some work on robustness of systems where input and output are continuous domains. For example, you have input that's based on some sensor measurement. And you can say things like, if the changes in the input are small, right, like numerically small, then the output should also stay within some small range. And that's actually very well studied notion, and that's been developed in control theory, but also in formal method. So in some sense, I think that addressed maybe your question, but we haven't seen sort of definition that also applies to discrete systems like software. So this is, I think, where our sort of contribution comes in, that, perhaps there's a way to combine those two different types of notions at some point, but right now we're focusing mainly on discrete systems. Good questions. Any other questions so far? All right, let me move on. Let me get to a punch, right? So why am I talking about this? What can I actually do with this, right? So I think the cool thing about this is that we can actually enable different kinds of analysis techniques or tasks that we couldn't do before. So here is let me sort of talk a little bit more about the analysis now. So here is a standard verification problem in formal method. So you have a model of the system, and you also have a model of the environment, and you have some property you want to check, and you have some tool like model checker that you can use to check, ask the question, does the system satisfy property under this environment? And the model checker will say, yes, it's satisfied. If not, then it may return a counterexample says why your system violates this property. So what our tool can do is we can take the same set of inputs, and it will compute for you, first of all, this delta, right? So what are the set of possible deviations that my system is robust against? Well, it can also tell you the set of intolerable deviation. So what are some ways in which the environment could deviate from expectations and could cause the system to violate its property? So in the case of DER 25, it can tell you, okay, here's a set of operator errors the system can handle, but here's also the other set the system is not able to handle. And those sort of different kind of information that's useful for different tasks, right? So you can use maybe information at the top to understand how robust your system is, but you can also use the information at the bottom as a way of improving or identifying areas in your system that should be improved for higher robustness. You can also do things like compare different designs. So if our tool that we built takes two different designs of the same system, and it will tell you what are situations in which one system may be more robust than the other. Okay? So one thing that actually Ian is doing is he has built models of DER 25, but also models of DER 20. And our tool can tell you, well, you can ask the question, is DER 20 more robust than DER 25 with respect to some operator errors? And then our tool will produce exactly those set of errors that they differ on, right? So again, these two systems may be safe under the perfect operator behavior, but they sort of start to show difference when the environment deviates from the expectation. And I think it's kind of cool because it sort of provides a way to rigorously compare designs with respect to robustness. Okay, so let me tell you a little bit more about how to actually do this, how to actually compute robustness. I won't go into a lot of details here, but there's two technical challenges that we need to solve. The first is that in general, there's an infinite number of possible deviations in the work, or in this sort of in our model. So how do we find the maximal set that the system is robust against? How do we actually compute this delta and the complement of delta? What we do is we actually leverage work that was done by other researchers, including Corina Pasaruna, who's one of our own. So they've invented this notion called weakest assumption for LTS. And this weakest assumption represents a set of all environmental behaviors under which system M satisfies P. So actually, by leveraging this concept, computing robustness itself is quite simple, well, not simple, but straightforward conceptually, in the sense that we first compute the weakest assumption, and then we essentially subtract the normative environment from the weakest assumption, and we get our robustness. We get the difference between the two as our robustness. Another problem that we run into is that, in general, this delta here is an infinite set of traces. And this is not a very nice sort of representation for the developer to navigate through. So we actually have a way of partitioning this space of possible deviations into different equivalent classes. And then we'll present these classes to the user instead of presenting all those traces. For example, this class 1 here, so different classes represent different kinds of deviations. For example, maybe class 1 represents a kind of operator error where the user omits an action. Class 2 represents a different kind of error where the user repeats an action. Okay? And what we allow is we can actually allow the user to provide a library of patterns of deviations in different domains. And our tool will use those patterns to represent the delta in terms of different classes that are mapped to these patterns. So for example, in the domain of human factors or human machine interactions, there's been a lot of research on trying to understand different kinds of human errors and trying to codify those errors into patterns. So for example, we actually have encoded a set of patterns that capture different kind of human errors based on this work, and then actually use that as part of our tool. So there are a lot more details here I don't have time to talk about, but if you're interested, we have a paper from FSC, or I can also tell you more about this afterwards. I'm going to move on. Any questions so far? Okay, so let me say just a little bit about the case studies we've done here. So we apply this definition of robustness to analyze different kind of systems. And one of the things we wanted to do here was we wanted to show that our definition can be applied to multiple domains. So not just the robustness against human errors, but we also wanted to look at a different domain, in particular, looking at robustness of network protocols against faults in the network. So let me just say a few words about that. So here, this is sort of the problem setting. Imagine that you have a sender and a receiver, and then the sender wants to send some signal. So the sender receives a sequence of inputs, and then they want to send it to the receiver. And then the goal here is that we want to make sure that the receiver receives the message in the right order as it was sent by the sender. Okay. And then we have our environment here is a channel. And the channel, what it does is it will essentially relay the message from the sender to receiver, and then relay the acknowledgement from receiver back to sender. If the channel is perfect, right? If the channel is reliable, it will do that in the right order. Okay. So what we did was we modeled two different versions of protocols that try to achieve this goal. So one we call naive protocol here, which is like the simplest protocol you can imagine. So what it does is it will send the message, and it will just wait for the acknowledgement from the receiver, and then it will send the next message. And then we also modeled a slightly more complicated protocol called alternating bit protocol, or ABP, which is a variant of sliding window protocol that's actually designed to be robust against certain kind of faults in the network. So under the perfect channel, both of these protocols will satisfy this property. But what we wanted to check was, can we actually reason about and compare their robustness if the channel begins to deviate, if the channel becomes unreliable and start doing things that you don't want to see. For example, the channel could, for example, duplicate a packet, right? Or it could perhaps cause some fault where some of the messages become corrupted. And we can, again, use the idea of traces to represent these deviations. So these are, so thing at the top here is the expected behavior of the channel. So it sends a message, relays that to the receiver, and then gets the acknowledgement from the receiver, and then relays that back to the sender. Now, we can represent the packet duplication as there just being an additional event that takes place. Or we can also represent the corruption as some of the messages being flipped, or some of the bits in the message being flipped from 0 to 1, for example. Okay. So then what we did was we took those two models, and then we actually asked the question, what types of faults is ABP more robust against? So is ABP actually more robust compared to naive protocol? And the output of the two told us that indeed ABP is more robust against messages being lost or duplicated. One thing that was so surprising to us was that ABP is also robust against acknowledgements that are potentially fabricated by a malicious network. And that was a surprising result to us that we didn't find in the literature. So that was kind of cool. And I guess the punchline here is that we can use our tool to rigorously compare robustness of two protocols. And we're very excited about this because we haven't seen any other tool that can do this kind of design comparison in a rigorous way. So let me conclude this part of the talk. So what we have shown is that our definition seems to capture deviations in different domains in software. And also just to give you some ideas about how our tool does, robustness can be computed under several seconds for reasonably complex models so far. Okay. So, okay, let me just conclude with the takeaway. So, so what we presented is robustness as, or our definition of robustness captures the largest set of deviations under which system can ensure its desired property. And by treating robustness as a first-class property of the system, we can do different kinds of design tests, such as analyze the impact of deviation on properties, understand the state operating boundary of the system, also compare different designs with respect to their robustness. So that was sort of the specification and the analysis part. So I'm going to move on and talk a little bit more about robustification. Before I do that, any questions I can answer? All right, so let me move on. Let me see how much time I have. Okay. Yep.
Yeah, hi, I'll ask one question. So there's also an aspect of robustness, some people call it resiliency, which is how well the system performs in the presence of a bad input. That is there graceful degradation? Can you measure how much deviation in the input gives you, what kinds of deviations in the input might give you what kinds of increments of degradation in the operation?
Yes. Actually, can I come back to the question? Because I have a slide about graceful degradation.
Yeah.
So maybe they will answer your question.
Okay.
Yep.
Why do you make a distinction between specification and robustification? Why robustness should be specified in specification? No?
Oh, so specification here means how do we say what it means for software to be robust? Robustification here means how do we actually modify the system to make it more robust.
Okay.
So they're slightly different
Yeah, I
problems.
see what you mean.
It will make more sense, I think, when I talk about robustification.
So the idea of robustness that you derive from a system also obviously depends on the model you're inputting, right?
Yes.
So how do you decide the right level of detail? Because due to that as well, your behavior E prime will also explode, right? If your model included some more components, I would say. So is there like an approach that you would suggest for that?
I mean, it's a great question. And that's actually like the $1 million question for us, because how do we build the right model that captures the right level of details? In general, every model is going to be incorrect to some extent, right? You're going to miss some details that you didn't think about. So I don't know if I have a great answers. I mean, one answer I can give you is that domain knowledge is very important here. So if you have sort of worked in particular domains of systems for a long time, then you have insights about what is the right level of abstraction that you need to use for your modeling. Another thing you can do is people have worked on things like extracting models from code or data from logs, operational logs. So that may help you sort of at least come up with the initial model for your system and then decide what to abstract away and what to include. So that may help. Eduardo? Yeah.
Yeah, I don't know if I understood correctly, but when Petrovsky talks about safety margin, okay, he's adding something for things he don't know or he doesn't anticipate. And here it seems like, it's something different. It looks more like failure mode analysis or something like that, where you have this model, okay, and then you start looking for some deviations. And if you're okay with that, that's okay. But I think that is very different from what Petrovsky says, well, I don't know what I don't know, or the famous unknown unknown.
Yeah, good question. Actually, I don't know if I agree with it. I think in the same book, he sort of talks about how we learn from failures, right? So failure is a very important part of engineering. And I think at least the way I understood this was that the things that you anticipate, okay, there's of course things that you cannot anticipate, but a lot of design process involves looking at the past, looking at past failures and trying to learn from those failures, what can go wrong in the future, right? So a lot of these deviations, knowledge about deviations, I think could come from failures. And I believe Petrovsky is sort of also arguing for that kind of process where, you again, you try to learn from your experience to derive these different types of deviations to anticipate. So we can talk about this more afterwards, but yeah.
So I think related to that, the elephant in the room is where does E come from?
Yep.
You model deviations and you showed a slide in which you used someone's taxonomy of the kinds of things that they anticipate. Can you say a little bit more about how in general you build models of E? Do you have to go out and find other people's domain analysis for typical errors in that domain, or can you go beyond that?
You could do, it's definitely, going off and looking at domain experts or getting domain knowledge is very helpful. But you could also, so I guess when you say E, you mean the
model of the possible deviations.
So I think, yeah, so I think that a lot of that, again, I will sort of use the same answer as I did with the other question. Domain knowledge is important, but also maybe you can learn some of this from data, or maybe by observing the system and trying to distinguish between expected behavior, normal behavior versus behaviors that look sort of abnormal, that are on the sort of boundary of what's expected versus not expected. So I'll say combination of two. I don't think you can do this without any domain knowledge at all. I feel like if you're coming into a new domain that you don't know anything about what could go wrong, it's going to be very hard to build a reasonable model of the environment and its deviations.
So is it part of the vision for your method to have techniques for obtaining that knowledge?
Yes, potentially. It's not in the talk, but yes, something that I would like to do. Yep, fine.
As a follow-up to, I guess, previous two questions, has anyone looked at robustification of systems or to make systems robust to modeling errors?
So, okay, that's a very good question. And there's a lot of work on that in other disciplines, like control theory. There's this idea of robust control. And they deal with two different types of deviations. So they deal with the deviations where the environment actually changes or there is a fault, like the kind that I'm dealing with here. But they also explicitly deal with model errors. The fact that you cannot always capture the environment perfectly, right? And they have ways of dealing with that. So how do you, again, build in some kind of margin into the system itself if your model may not be very accurate? And I haven't explored that much, but it's also another interesting problem. All right, thank you for the question. Let me move on. So I'm going to talk a little bit about robustification. So what am I talking about here? So the problem here is that, okay, you have your environment E, and again, it deviates, right? So you have new environment E prime, and there are some deviations that we cannot tolerate, okay? So idea is that we want to find a way to enhance the original design, the system, such that now it becomes robust against those deviations. So, and question we asked was, can we even maybe semi-automate this process, right? Now, if you talk to Claire, she will tell you that everything is program repair. And Claire's right, I think. Anything that Claire says is correct. So we're going to think of this as a model repair problem, right? So how do we repair this model such that it becomes robust against the deviations? Now, the challenge here is that this is actually a very hard problem because there's, in general, an infinite number of possible ways you can modify your system, your model, right? You can do things like add, remove transitions, add, remove states, and this sort of space of possible transformation is unbounded. So how do we solve this problem? What we're going to do is we're going to sort of delegate this to another problem. We're going to use the problem of robustification to a problem of what's called supervisory control. So this is actually a very old problem. This was, in fact, a subfield of control theory where people have studied how to design controllers over discrete event systems. And the basic idea here is that you have what's called a plant. A plant, you can think of this as a system that you want to control. And then you want to synthesize the supervisor such that the plant under the control of supervisor will satisfy property P or enforce the property P. So how does this work? So conceptually, the way this works is that the plant or the supervisor is going to observe the plant's behavior. So it's going to continuously look at or access the history of events that are performed by the plant. And then it's going to try to infer the state of the plant based on that sequence of past actions or events. And based on the current history, the supervisor will decide to disable some of the actions that may be performed by the plant. Right? So now the plant ends up with some subset of events that it's allowed to do at a particular state. Okay? So just give you an example. Suppose that you have a manufacturing robot that has an arm that does things like pick up an item from a conveyor belt and maybe move it and then put it down somewhere else. So suppose you want to synthesize a supervisor to do this. So the way that would work is that the supervisor observes the history of the robot actions in the past, and it will try to infer the state of the conveyor belt based on those history. And then it will decide what actions are safe to perform in that particular state by the robot, and then only enable those actions to be performed. And by doing this, idea is that again, the supervisor will enforce the property that there's no, let's say, incorrect assembly. And this idea has been applied to many other application domains, such as network security, concurrency control, synthesizing protocols, and many others. So again, if you're interested in this topic, I'll be happy to talk to you more about this afterwards. So going back to this idea here, so we want to reduce the problem of robustifying system to synthesizing a controller. So the way this is going to work, we're going to, again, go back to our picture here. We have M, our system, and the E prime, which is our deviated environment. And right now, the system does not satisfy P under this new environment. We're going to treat software and the environment together as a plan. Okay, so the composition of those two components is going to be the plan for us. And then we're going to synthesize a supervisor that's going to try to enforce the property over this plant. Okay. So let me go back to example. So going back to Direct 25. So here the M is the Direct 25 design, and the E is E prime is the environment with that captures the error that could be made by the operator. And then what the supervisor that we try to synthesize does, it will essentially try to look at the actions, the behavior of the user, and they will try to disable certain events if it thinks that it's going to lead to an unsafe state. So let's move back to the example here. So the violation that I showed you was that the system is in transition from X-ray mode to the electron beam mode. So it's kind of stuck here, but the user fires the beam at this point, even when the spreader is out of the place, right? So that was a safety violation that was caused by the operator error. So what the supervisor does, or we want to synthesize a supervisor that tries to prevent this particular action of the operator that could lead to a safety violation. And the way this works is that it's going to, again, keep track of the state of the system. So here, the state of the system consists of the state of the interface as well as the state of the component that changes the radiation setting. And then what it does is that when the supervisor notices that performing a particular action could cause the system to go into unsafe state, it disables the action. Okay, so it doesn't even allow the system to perform that action. And it only allows other actions to be performed by the system. In the particular case, the set action is the one that indicates completion of the mode switch from X-ray to the EV mode. So in the other case, this supervisor will enforce the system to wait until the mode completion has been done, and then only then allow the user to perform other actions. Now, in general, so this seems fairly straightforward, but in general, this is actually much more complicated. So the problem here is that not all the events in the system may be observable or controllable by the supervisor. And also there could be non-determinism in the system itself, meaning that the supervisor does not always know exactly what state the system is in. So he has to keep track of multiple possible states of the system and still make actions or still decide which events to disable based on those possible states of the system. Okay, so once you do that, once you synthesize the supervisor, the next step is we're going to basically combine the S and M, okay? And that composition of S and M will become our new design, the new machine that we're going to replace the existing design. And then we'll ensure that the property is satisfied under the deviated environment. Okay. Any questions so far? Yes, yeah, Ben.
Is this always possible, or is there just situations where it's impossible to generate this supervisor that establishes a property?
There is possible there is no solution. Okay, depends on which events the supervisor is able to control and observe. If he cannot control anything, then in general, that's not gonna be possible to satisfy any property. So it kind of depends on, yeah.
Back at the introduction of the idea of a supervisor, you said that the supervisor can disable certain actions. And I certainly grant that having a solution that works sometimes is better than having no solution. And so it would be unfair to ask for each of your innovations to be complete. But at that particular point, I wondered why it was just reducing the set of operations. Rather than, for example, enabling operations. There might be operations in a plant that are undesirable, like, vent excess gas into the air and report the pollution violation, but that's better than exploding.
I see.
Or invoke emergency shutdown that stops the assembly line entirely. So I wondered whether it was important that you only reduced the set of available operations rather than, for example, enabling operations that are undesirable but would still render the system safe.
So, again, if I understand your question correctly, but the way I think about this is that all the events are enabled by default. And the supervisor will choose to disable some subset of those events. And if, let's say, there is an event in there in the original set that could allow this type of maybe graceful degradation, then the supervisor will not disable that. It will sort of allow those events to be taken place or to be performed by
Okay, so your model is that the entire set of operations is available
Yeah.
to the software in the first place, including the undesirable ones.
including, yes.
So,
basically any- yeah.
Emergency stop would be part of the software itself rather than something that's available primarily to the supervisor.
Yes, all the supervisor doesn't actually add new events. It's only looking at available set of events and then decide, okay, which one of these should be disabled versus left enabled for the system to use.
So the old control system idea of very inverted pendulum. You've got the super smart controller that nobody can quite figure out. And then the supervisory controller that's dumb and simple, but verifiable. You know that story.
Yep.
How does that story fit with this structure?
Good question. I don't know whether we actually have any smart supervisor here. The supervisor here, we only have one supervisor here, right? That the system is already sort of broken or not quite robust enough, and we're adding additional layer on top of that to make sure that for certain unexpected deviation in the environment, that supervisor steps in and will try to make sure that your system is safe. So in that sense, I mean, I have to think about this a little bit more, but I don't sort of, there's only one supervisor here in some sense, right?
But it's an inhibitory
Yes.
engagement rather than the supervisors stepping in and actually taking an action.
That's true. It is sort of, it inhibits certain kind of actions. But we try to achieve safety by disallowing some action in the system. Yeah. David?
Doesn't this follow from the fact that P is a safety property? Not unlike this one.
Yeah.
So maybe some of the concerns here is obviously you can disable everything, and then you wouldn't have a problem.
Yeah, actually, I'm going to talk about that next. Yeah, let me get to that. I think I will answer your question there. So for the there are 25 examples, the solution that they synthesized here will essentially add additional check to wait for the system to complete the mode transition, and only then allow the user to press B to fire the beam. Right? So, and this would ensure the property that I presented before. Or this would fix the problem with the violation. Now, as David pointed out, there's actually multiple possible solutions to this problem. And the one of the issue here is that we give the supervisor the choice to disable any subset of events. And what that means is that sometimes it may choose to disable more events than needed. In fact, if the property you care about is safety property, then a supervisor that disables everything is a very safe supervisor, right? But it's also not very useful, right? So what we want is, in general, we want to find a solution that preserves as many of the existing behaviors in the system as possible. So we call this sort of permissiveness. At the same time, we want to ideally pick a supervisor that is simple, right? We don't want to sort of incur too much cost in modifying the existing system. Now, it turns out that these sort of two dimensions of robustification method or solutions, they're kind of in conflict. They're sort of different so this results in this multidimensional space where if you want to find a very simple supervisor or solution, that tends to result in a system that's less permissive. Whereas if you want to find a very permissive system, that often requires adding more complexity to the supervisor or the solution or the redesign that it comes up with. So what we do in our approach is that we actually will compute this Pareto optimal for you. We will actually enumerate all these solutions for you, and you can look at them. And depending on the trade-offs that you're willing to make, as a designer, you can choose one of these solutions as the final one to implement. So I'll give you an example of this shortly in the next few slides. So we actually implemented this as a tool. In fact, we have a framework that combines the robustness analysis with the robustification tool or technique. So the way this works is that the designer starts by analyzing the robustness of their system, and perhaps there is some deviations that it cannot handle. Then they can use our robustification approach to generate candidate solutions, candidate method or ways of modifying the design. And then they can take a look at those and then choose one of those solutions and then repeat the process until they reach a system that they're happy with. So there's a lot more details that I can talk about. This work will appear in ICSI this year. And if you're interested, again, come talk to me afterwards. So let me just say a little bit about the case studies we've done. So we apply this idea to two different kinds of systems, one electronic voting system, and another one infusion pump. So let me just say a little bit about the electronic voting system. So this actually is based on a real voting machine or voting software called iVotronic. In fact, I think this is still used in the US. And the reason why we picked this system was that there was actually an election fraud involving this particular voting machine. This was somewhere, I think, in Kentucky in late 2000s. So what happened here was that, so in the system, the voters walk into a booth and they make their choice, and then they're supposed to press confirm to finalize their vote. Now, it turns out that some of the voters forget the last step, so they would just forget to press confirm, and they walk away from the voting booth. And this is actually a very common error. This is called post-completion error in human factors. And so this happens with things like ATMs where people forget to take their card after taking their cash, for example, right? So what happened was that in this fraud case, some of the election officials were actually malicious. They had a malicious intent. So they would walk into the booth after the voter has left, and they would press back, and they would modify the votes, right, to their liking. Eventually, they got caught, but then, again, this is bad, right? This should not happen. So what we did was we wanted to see whether we can apply our technique to improve the design of this system, okay? So what we did was we modeled the interface of the electronic voting system, and then we expressed a property that says things like the machine must record the vote as selected by the voter, not by someone else. And then we introduced a deviation that allows the voter to skip that last step, okay? And then we use our tool to generate solutions to improve this design to address the potential fraud where the election official walks in and then changes the vote left by the voter. So here's sort of two solutions that are generated by our tool. And again, this also demonstrates the trade-off between complexity and permissiveness. So this solution here is very simple. What it does is just disables back button, right? And this works because if you disable back button, then the election official who tried to change the vote cannot change it, but there's no way for them to go back. So this will actually ensure the security property we care about. But this is also kind of not very nice solution because, well, now the voter cannot change their vote, right? So it's not as permissive as we would like. So another solution that our technique will generate is something that looks like this. So what it does is it will, instead of disabling the back button, it keeps track of who has entered the booth. And then it will disable confirm button if the election official is in the voting booth. Okay. Okay, this also works because let's say the election official is in the booth, and if they cannot press confirm, that means they cannot finalize the vote, and therefore they won't be able to change the vote that was made by the voter. And so this is much more permissive because this allows the voter to still press back and change their vote if they want to. But it's also much more complex design because it requires the system to keep track of who has entered the voting booth. So again, the idea here is that these are different kind of solutions with different trade-offs, and our technique can generate all these things for you, and you can look at them and decide, okay, which one of these, which of these trade-offs I'm willing to make. Right, and then just a few words about performance. So for, I think, moderately complex models, we can synthesize the solutions under 20 seconds. We haven't actually tried this to very complex systems, but so far we are happy with how well this technique scales. So I can tell you more about the technical details of this approach afterwards.
One question about that?
Yep.
So the ATM designers came up with a very clever solution, which was force you to take your card back before you take your cash. If you're doing cash withdrawal.
Yeah.
So you don't leave the card because the valuable part of the transaction from the user perspective happens only after the card is returned.
Right.
Is that something that could be synthesized by the supervisor here?
So ours, no, we don't. And actually, I don't know what that would look like in this context.
Because you're reordering the
Yeah.
the elements of the protocol.
We are, but I don't know there's any, like here, there's nothing like cash here, right? That would encourage the users to wait for, right? Like in case of ATM, I'll wait until I take the cash because that's what I came here for, right? Like I'm taking out the money, and if I don't have the money, I'm not gonna walk away. Whereas in this case, I don't know what that would look like.
Could your system do the ATM? Could your system generate the ATMs?
We haven't tried it actually. That would be interesting to try. Yeah. Good, interesting question. Okay, let me conclude with, okay, I'm just gonna spend like 2 minutes talking about some other works that we're doing, and then I'll conclude the talk because we're over time already. So I talked about, okay, I just talked about robustification, which is the process of improving the design of the system. Now, another way to make the system more robust or deal with deviation in the environment is instead weaken the property. So this sort of goes back to, I think, Bill's question about graceful degradation, right? So if the system or if the environment changes, instead of trying to change N, can we weaken the property such that to the extent that it's acceptable to the user, and that is satisfiable in the new deviated environment. So we're sort of building a process based on self-adaptation to try to allow this type of property adaptation so that system can still function even in the environment they didn't quite expect. And this is a work that's led by Simon and CJ, and also in collaboration with Gabe Moreno at SCI. Another work we're doing here is we're looking beyond just software. We're looking at robustness of systems that contain both machine learning components as well as non-machine learning components. And here the questions are things like, can we reason about the robustness of the system against deviations, but also mistakes that could be made by machine learning components? And what does it mean for systems to be robust in that sense? And how do we test this? How do we measure this? And lastly, another kind of work that we're doing is looking at robustness against feedback loops. So far I talked a lot about deviations in the environment. Now, one question is, why those deviations occur in the first place? Sometimes they occur because the environment just changes organically. Sometimes these are caused by the system itself, right? The system makes a decision that influences the environment in some ways, and then which they in turn interact with the system. And sort of this kind of feedback loop can over time be turned into something called self-reinforcing feedback loop. And some of these self-reinforcing feedback loops can cause negative side effects on the environment. So we are studying ways to model this kind of feedback loops in machine learning-based systems, monitor these feedback loops, and intervene if we notice that the system is causing a harmful effect on the environment. And this is doing work with Simon, my postdoc, and Yining here in the audience. So what I presented to you today is some of the questions that we're trying to answer with respect to how do we understand the robustness of software systems, how do we analyze it, how do we make it more robust. And just takeaway is that it's something that I think we should think a little bit more about, right? Like a lot of systems we build are making often implicit assumptions about the environment, but in practice, the environment will deviate, right? It will fail to satisfy those assumptions at some point. So the question is how they design systems to be more robust against those deviations. And I think there's a lot more work to be done here. And with that, I'll end and take your questions.
So for the computation of that Pareto frontier, you rely on enumeration of the possible supervisors.
Mhm.
And so that kind of relies on the fact that these are LTSs and
Yeah.
that's cheap. Are there other models that are more, that are in a different complexity class where this is harder or impossible?
Actually, even with the LTS, it's very expensive. It's like exponential complexity, it turns out. So we have a lot of heuristics that we developed to make this process reasonably efficient. And as for other complexity, other models like hybrid models that also have some elements of maybe continuous behavior, it will be even harder. So, so that I guess a short answer is yes, it's a very hard problem. I think it's relatively easier for LTSs. For other kind of systems, probably much harder, and we need different kind of heuristics. Any other questions? Yeah, great.
I have some other questions. At some point you said that the safe but drastic operation is to disable all operations.
Yeah.
I want to challenge that. Going back to Levison's book, there's another example in there about a chemical plant that blew up. And the punchline of the story is that the emergency operation was supposed to keep all the variables constant, that is, in effect, disable all operations. But the situation was that the tank was going over pressure and the valve to introduce catalyst had just been opened. And by not closing the valve that was introducing catalyst, accelerated the rate of the reaction and it went bang. So sometimes the right operation is to go into a mode in which you're trying to hold the pendulum upside down and keep it under control by chasing a process that's going out of control, but you're doing your very best to get it back into some degraded but not drastic region.
Yeah.
So in general, I think that's a little simplistic to say your safe operation is to shut everything.
I agree with you. I see in some sense, so the supervisor here is sort of, you achieve this goal by restricting behaviors, but that's not always what you want. You actually want to encourage certain kind of a recovery behavior if something goes wrong in your system. And that is not handled by this particular kind of technique.
So there's two ways of dealing with bad things. One is to prevent them from happening, which is what you're doing. And the other is to observe that they have happened and remediate, which is what this example is talking about. And in fact, it's what insurance is about. You try to compensate people for the bad thing that happened.
Yeah.
And it seems to me that you're sitting on the prevention side. And I'll suggest to you that there may be an interesting set of problems on the remediation side.
Actually, I only talked about the prevention side, but Simon is working on the remediation side. So more work to come there. But you have a very good point. That's a very good point. Yeah, Johnson?
So I think that's a really interesting question and conversation. And as a follow-up, I noticed that most of the properties you talked about were essentially safety properties, right? But in formal verification, we also sometimes consider liveness properties. I wonder, Have you looked at liveness properties at all? And might liveness, thinking about liveness play a role in addressing some of these scenarios where you want something to happen?
So answer is we have not looked at that much. It's something we want to do next. We only look at mainly safety properties. And also I think it would address some of the questions that Mary has raised, right? So again, it's not about preventing something bad from happening. You want something good to happen eventually. For example, if your system's in a bad state, eventually you want it to go to a good state. That sort of has the liveness flavor, right? And that right now is not handled by the framework here, but something that we're actually looking into to extend. Cool. Yep.
On this subject, if we take into account the fail-safe default property of cybersecurity, you were talking about state machine. Like, wouldn't it be simpler to model like what you want from the software as a state machine and just like cancel every deviation from it, than model what possible deviation and like try to evaluate if they are acceptable or not deviation? You know what I mean? Like, I mean, the software is supposed to do something, just let it do only this, you know? Like with your example of the machine, if we do B, if we choose X-ray, we just go until the end before it being able to start again, instead of the button back. You know what I mean?
Right. So let's see. Let me understand.
Like model the state machine and just allow only available actions instead of like potentially allow deviation that could.
Oh, you mean try to prevent the deviation from happening in the first place?
Yeah, like allow no deviation.
Oh, okay. That's a good question. So in general, there's something I didn't talk about much is that we have the environment here, right? And we're assuming that the environment is not really controllable by the system. So environment will just do whatever it wants to do, right? It's outside of the control of the system. So in that sense, there's only so much the system can do to prevent some of these deviations, right? For example, if the user wants to press some button, they will do that, right? There's no way you can stop the user from, at least the software cannot stop the user from doing something. And that will just be part of the model that you have to consider, I think, right? Yeah, so I don't know if that answers your question. So the answer is that yes, ideally yes, but we can in general because we don't have control over the environment.
Okay.
And that's kind of a classic separation in design, right? That the thing you're designing is the thing you have control over, and it has to exist in an environment that you don't control.
Yeah, exactly. CJ.
Yeah, so in fact, I want to follow up on Mary and Jonathan's comments. So sometimes I find like safety property and liveness property in formal reasoning is different from the safety requirements we're talking about. So for example, in Mary's case, if we want to formalize that property, it will be some liveness property that we want to reach some good state by leaving some dangerous state. So in formal reasoning, that will be a liveness property, but even though in reality, that's more like a safety requirement. And another thing is we haven't looked into liveness because liveness is often a harder problem because so as Mary said, right now we are standing on the prevention side. But if you so prevention is more like disabling actions. But if you want to enable actions, then the search space would be even larger, and often infinite because we don't know what we can actually do. So if we want to search for infinite number of things we could do, then the problem becomes harder and harder. So that's a reason that we haven't looked into liveness. Yeah, but I think we will in the future.
David?
Another possible extension of what you're about this is to move into a probabilistic domain, in which instead of eliminating the problem, you reduce the likelihood of it occurring.
Yep.
And that's a different kind of robustness, but it seems like it might be amenable to the same potential techniques.
Yep. No, yeah, that's something else on the list. A long list of things we want to do. We have enough people for. So if you're interested, I mean, please talk to me. We've got a lot of problems here that I would like to solve. So.
All right. Well, let's thank Eunsuk again for